Inverse functions and their derivatives. Well, first we're going to start with inverse function, which will be quite a bit of college algebra review actually, and then we'll get into the derivatives part. Now whenever we work with derivatives, we know that we're talking about slopes of tangent lines, and so that will be kind of where we end up. So a couple different things here. Whenever you see the S with a P hanging from it, this means suppose. It's kind of a shorthand notation. So whenever you see that, it means suppose. So here, suppose f of x is a function, then the inverse of f of x is denoted f inverse of x. Okay, and let's do an important note here. A lot of times when you see that negative in the exponent, you might think, oh, I need to flip that. But that's not the case with this notation, and it's not the case with your inverse trig functions either. So this is not equal. These are not equal to each other. So when you see that notation, don't flip it. Okay, and again, it works the same with a trig function. So if let's go ahead and do the college algebra review. A function has an inverse if it passes the horizontal line test. Now remember, if we wanted to know if it was a function, we use the vertical line test, but this is the horizontal line test to see if it's an inverse. So let's look at some examples. Okay, let's look at this graph. Just throw a few up here. So that's a quadratic. This is an exponential growth. This is a third degree polynomial parent graph, and this is a square root graph. Okay, so this first one is a no. Now it is a no because when I run the horizontal line across here, I hit 2 points. And this happens a lot, but it just has to happen one time for an inverse to not exist. Now let's look at the next one. Passes the horizontal line test. So does the third degree polynomial, and so does the square root graph. So these are all yeses. Now if we have a graph that we're interested in looking at that does not have an inverse, for instance this first one, a lot of times what we can do is say, well, I'm going to consider this graph, but I'm only going to consider part of it. Because if I consider this right-hand side of this graph right here, then it passes a horizontal line test. So I can turn the no into a yes by restricting the domain. So this is a graph of y equal x squared, and what I'm going to say is I only want to look at this when my x values are between 0 and infinity. So when I do that, now it is a yes, the inverse exists. So by restricting the domain, now I have an inverse. Let's go ahead and look at a trig function. Let's look at y equals sine of x. We'll look at this in terms of radians. So I'll have pi over 2 pi, 3 pi over 2, and 2 pi. And our max point is 1, min point -1. So the sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is -1, and the sine of 2 pi is 0. And that's from your unit circle. If you need to refresh your unit circle knowledge after summer, that would be great. It's going to be really important that you know your unit circle. It needs to be memorized because we use these all the time. So if I look at this particular graph, it does not pass the horizontal line test. It has problems all over the place. Now also with the trig function, we have to remember that it goes in the negative direction. It continues the same pattern. So this would be the point negative pi over 2. This would be negative pi. Okay, and this would go on forever in either direction following that same shape. So the question on this one is, where do I restrict it? Well, I could just restrict it from negative pi to negative pi over 2, because that passes the horizontal line test there. And I could do from pi over 2 to 3 pi over 2. So what ends up happening is we have agreed upon where we will restrict the sine graph, the cosine graph, and the tangent graph in order for inverses to exist. And this is review from trigonometry, but I want to bring it up because it is an important point. So the way I decide to restrict it is between negative pi over 2 and pi over 2. So if I only consider this part of the sine graph, I can see that an inverse will exist. Isn't that cool? So here's my inverse that exists here now. So the sine graph does not have an inverse unless I restrict the domain. So when I restrict it, yes, the inverse exists. If we restrict the domain to negative pi over 2 to positive pi over 2 points inclusive. So points inclusive mean bracketed values, meaning I can actually reach these endpoints, negative pi over 2 and positive pi over 2. So there would be one of these for cosine, tangent, and there's actually one for secant, cosecant, and cotangent as well. But just to bring it up, that a trig function actually doesn't have an inverse unless you restrict the domain. Let's go ahead and look at some properties of inverse functions and their inverse. The most important one that comes up a lot are the domain and the range swap. So this would be the same as saying the x and y swap. So let's say I had some function. I'm just going to make up a few points here. And I'm going to talk about input and output here instead of domain, range, or x, y. And the reason I want to do that is I don't want to get hung up on x's and y's, because when they switch it gets a little bit confusing. So we need to understand that input is domain and output is range. They're interchangeable. And let's look at these values. So for my input I'm going to have 1, 2, 3, and for my output I'll have 4, 8, 12. So this is the ordered pair 1, 4, 2, 8, 3, 12. Okay, so let's go ahead and come down here and let's graph those. And then we'll graph the inverse points too. So again, the 1, 4 is an ordered pair, so we go over 1 and up 4. Then we go 2 up 8, and then 3, 12. Okay, so this is my original function that I'll call f of x, and I want to connect these points. So this is f of x. Now if I continued on, I could find more points on this following the same pattern. And the pattern here is 1 times 4 is 4, 2 times 4 is 8, 3 times 4 is 12. So it's basically my slope is 4. Okay, now let's go ahead and come up here and let's look at the inverse. So if I look at f inverse of x, like we said, the domain and the range swap. So again, instead of getting tied up with x's and y's, I'm going to think of this as input and output. And if you want to also consider that as domain and range, you can. So this would be 4, 1, and that switches from right here from 1, 4. Then we'd go to 8, 2, and 12, 3. So let's go ahead and plot these points. So here's 4, 1. Now 4, 1 is the reflected point of this one, 1, 4. Okay, the next one that we want to look at then is 8, 2. And 8, 2 is the reflected point of 2, 8. Okay, next one would be 12, 3. And 12, 3 is the reflected point of 3, 12. So they all have this reflected point. And in fact, they reflect across the line y equal x, which bisects the first quadrant at a 45-degree angle. So y equal x means here I am at 1, 1, 2, 2, 3, 3, 4, 4, etc. So that's our next characteristic. Let's connect these dots though before I go for that. So we can see that if we were to fold this, if this were a piece of paper, and if I could fold it right along this line, these points would match up. These are the reflected points. Okay, so that's another characteristic, is that the graph reflects over the line y equal x. Now a lot of times when we're working with inverses, just because the notation is cumbersome, a lot of times they'll replace f inverse of x with g of x, but it has to be defined as such somewhere. So if you ever run across that, you might want to consider that alternate notation. So the graph of f of x and f inverse of x reflect across, or a mirror image across, the line y equal x. Okay, so those are two very important characteristics. Now what we did here is we just plotted points. I don't know my original function. I could figure it out probably because they're just straight lines, and we can always figure out the equation of a line given 2 points. The thing is with an inverse, usually you can't find an inverse. So that's kind of the tough part of this. So that's why the calculus is going to come into play to help me evaluate inverse functions without ever seeing them. So it's kind of a strange idea, but that's where we're shooting toward, is learning enough about inverse functions so we can eventually evaluate the derivative of an inverse function without ever actually knowing the inverse function. Okay, so now let's go ahead and get back to some algebra. We're going to look at how to find the inverse, and again, this is algebra review, but I think it's important to do so we can relate the two topics of inverse functions and derivatives. And again, please take note, usually it's not possible to find the inverse. Just for basic functions it is. So let's look at a few. So when we talk about finding the inverse, let's look at a graph like y equal 1 over x. I can find the inverse. And we'll go through y when I put enough of these up here. Let's look at y equal x cubed plus 4x squared plus 2x minus 5. Can't find the inverse there. Let's look at y equal tan 3x over 2 plus 4x minus 9. Now let's look at the steps for finding an inverse, and then you will see why we can go back up here and say yes, no, no to these. So let's look at the steps for finding an inverse. Now usually the first two steps are good. It's the third step that causes trouble. So the first step, what we do is we replace any notation that has f of x with y. Because f of x means the y value, it means the output value, it's just functional notation. Next we swap x and y terms in the expression. Okay, now third, this is this tough part. We solve for y. And then our last step, we would replace f inverse of x notation, replace f inverse as x notation for the y value. Okay, so let's look at this one, this first one up here. This would be pretty straightforward. So I would swap the x and the y. So I'd have x equal 1 over y. And solving for y here is easy. I'd multiply both sides through by y. And I'd get xy equal 1. And then I would divide both sides through by x. So I get y equal 1 over x. So that was easy enough. So this is a yes, I can find an inverse. Okay, now this next one, I can swap the x and the y. But I can't solve for y. When I look at this, there's no way that I can get y all by itself. So it cannot solve for y. So what ends up happening here is there's no inverse that can be found. There's an inverse out there, but I can't just explain it using some sort of functional notation. I can plot a lot of points, meaning I could find lots of ordered pairs for this and then reflect the points and then sketch it, but I can't find a function that looks like the inverse of this that's easy to describe that I can take the derivative of. So that's where we're heading toward. We want to be able to take the derivatives of these things, and if I can't even find them or define them, that's tough to do. Kind of a neat idea. Okay, now here let's go ahead and swap as here as well. Same problem. There's no way I'm going to get y by itself. Okay, so I cannot solve for y. And I shouldn't say there's no inverse. I'll say no inverse easily found, meaning I can't find a function that describes the inverse. I could just plot a lot of points and I could get a picture of it, but I can't figure out what it would look like. So no inverse easily found here either. So let's look at some functions and use these 4 steps to find the inverse of them. We'll start with kind of some basic ones and we'll get into some tougher ones, but again, these are all just going to be pretty basic functions to work with, and it's all just a lot of algebra. We'll also look at a graph, and when we look at this graph, we're going to try and look at it and decide whether the graph is a function and its inverse. So let's look at that first real quick before we actually find an inverse. Okay, so let's look at this graph. Now, a couple quick things. This is pulled straight from my math lab, so this is something like a problem that you would see in my math lab. And if you're like me, you might have problems reading these teeny tiny little graphs. I just want to point out that up here, the magnifying glass, I can enlarge the graphs to make them easier to read. And then this little pop-out icon makes the graph pop out from the page in a separate window that's easier to read as well. So if you're having problems reading the graph, make sure you use some of those features to make it a little bit easier to work with. Okay, so decide whether the pair of function graph to the right are inverses. So what we have here then is the line y equal x, so it should fold across that, and it does look like it folds across that, so that seems positive. So now let's look at our red line, and let's call that f of x. So this is going to be f of x. And let's just find some ordered pairs. They don't have to be exact, just kind of a ballpark. So here's a nice ordered pair. It looks like -2, -5. Okay, so -2, -5. And I want to find another one right here. I want to find ones that are easy to describe. I don't want fractions if I can get away with not having fractions. So -1, 1. And here's 0, 2. And it looks like there's one more right here that would be easy to describe, and that looks like 1, 3. So the question is now in the blue line, it's kind of a bright blue. Let's see if we can find a brighter blue. This should be my inverse. So this line is f inverse of x. So what should happen then is these points should swap. 1, -1, 2, 0, 3, 1. Okay, so now let's check each one of these to see if it actually lies on the blue line. If it does, then it really looks like they're probably inverses of each other. So -5, -2. So here's -5, -2. So there's that point. So that checks. That seems to be on there. And then 1, -1 is right here. That's on there. 2, 0 is on here. And 3, 1 is on there. So each of these points that we just described are on the inverse. So for this one, I would say yes, they are inverses of each other. Now I don't know what the functions are. I'm not sure what it looks like in terms of x squared, some sort of a trig function. Not sure. I don't know what it looks like, but I can compare point by point. Okay, so that's a possibility. Even if you don't know how to name the function or describe it, you can graph it, which is kind of a strange idea. I kind of like that, something unknown. Okay, so for this first problem that we're going to look at, we're going to determine whether the function is 1 to 1, and then we will actually determine the inverse if it is 1 to 1. And 1 to 1 just means it passes the horizontal line test. So we want to say everything we can about this function from the beginning. So this is our original function, y equal x cubed minus 3. So a couple of things here. We need to determine whether it's 1 to 1, and 1 to 1 means that it passes the HLT horizontal line test. Okay? Well, you can graph this on your calculator if you'd like. This is a third degree polynomial that's going to cross right about here. So this is what your graph will look like. And this does pass a horizontal line test, so it passes, so it is an inverse, or an inverse does exist. And again, the question is, can I find one? Well, this is a pretty basic graph, so I kind of feel like we're going to be able to because they give us that function. So the next part of this would be to actually find the inverse. So we're going to follow our steps. So the first step is to replace f of x with y. And hopefully this looks pretty familiar, something that you've done in college algebra. Second step is we swap x and y. Third step is we solve for y. So in solving for y, we want to isolate the y. So I get x plus 3 equal y cubed. And I always like the variable I'm solving for on the left, so I'm going to flip it around. And then our next step would be to take the cubic root, or raise it to the 1/3 power. It's the same thing. Cubic root and then to the exponent 1/3 is the same. So here I'd get y equal x plus 3 to the 1/3. Now if I wanted to rewrite that in radical notation, that would be the cubic root of x plus 3. So either one of these would be considered the inverse. And then our fourth and final step is I replace y with f inverse of x notation. So f inverse of x equals the cubic root of x plus 3. Okay, so there is my inverse. Now when you enter this answer in my math lab, usually they have this box given and then they just show a blank, so you would just put in this side. So just be careful that you look at that and you don't put in more than they're asking for. Okay, so the function was 1 to 1. 1 to 1 means it has an inverse. It passes the horizontal line test. And then what I'd like to do also is come up here and I would like to talk about the domain and the range. And this is not very exciting for this problem because the domain and the range are all real numbers. So we're going to run into some problems where it's a little bit more exciting. So let's look at the function f of x and f inverse of x. When we look at this, there's no restrictions on this. There's no square roots, there's no denominators, there's nothing to restrict this function. So the domain is all real numbers. Now remember what we said, between a function and its inverse, the domain and the range swap. Okay, now the range for this graph as well is negative to positive infinity, and it swaps here too. Okay, so it's not very exciting because they're all the same. It's hard to see the difference when, you know, everything is the same there. So that's my domain and the range. And then if you want to, you can go ahead and look at a graph, and I'm actually going to pull up the graphs, the options that they give us for this problem. Okay, so let's have a look here. Now remember, the domain and the range swap, the x and the y values swap, and then also it has to reflect across the line y equal x. So let's look at each one of these. Here's the line y equal x, and it does, this part A does look like it reflects there. Let's put y equal x here. This does not look like it reflects, so let's draw this in. That does not look like this reflects across that line very well at all. And then let's look at the third one here too. It misses that point where it crosses. So I feel like just based on the y equal x line, that B and C are going to be incorrect. Now let's look at some points here. We can see this point reflects across, this point reflects across. So I'm seeing all these reflection points. And so I think our answer here is A. Actually, let's check. Yep, it is A. So there's the function and its inverse. We talked about the domain and the range. And I want to do one other thing here. So this is another, I guess, characteristic I should have put up in here. It's just a real quick one. So to determine if it's a valid inverse, what ends up happening is when I plug the inverse into my original function, I get x back. And when I plug my original function into my inverse, I get x back. So these both must be true in order for them to be inverses of each other. So that's a little quick one there. So I'm going to come down here and actually do that and show you what that looks like. It's kind of cool. Okay, so check or verify, I'll call it verify inverse. So I have my original function, in this case was f of x equal x cubed minus 3, and then my inverse function that I just found over here was a cubic root of x plus 3. Okay, so first one I'm going to check. I'm going to check f of f inverse of x. That means we're going to take this and plug it into that. So let's do that. F inverse of x is a cubic root of x plus 3. And this says to plug it into my function f. So I'm taking the cubic root of x plus 3 to the third power and then subtracting 3. And this f notation is actually gone because I plugged it in. Now what ends up happening here is the cubic root and the third power cancel each other, and I'm left with x plus 3 minus 3, which equals x. So this one checks. Okay, let's look at our second one. This would be f inverse of x is my main function, and then I'm going to composite that with f of x. Okay, so the way this looks is I will take this function and plug it into this function. So my cubic function, and here will be my thing I'm plugging in, and then I'll add 3. So I'm going to plug in an x cubed minus 3 from here and plug it in right there. So let's simplify this. Excuse me. So minus 3 plus 3 cancel, and I'm left with a cubic root of x cubed. The root and the power cancel, and I'm just left with x. So this checks as well. So that verifies that they are inverses of each other, and that's usually just an algebraic process to establish that. And it can get a little tedious with a lot of algebra, but it's I don't know, it's very nice at the very end. It's very satisfying when you get this x at the end, no matter how ugly it is what you start with. Okay, we're going to do the same thing for this one. Now again, if you want to graph this on your calculators, you can. If it's kind of interesting on your calculators, they just know how to connect the dots. They just plot a bunch of points and connect the dots. And there's going to be a gap in this one at x equal 4. And there's also going to be a horizontal gap at x equal 1. So that's from knowing the domain and knowing how to find horizontal asymptotes and vertical asymptotes. But this graph will basically look something like this. So again, there's a vertical asymptote at 4. Now your calculators typically don't have this dashed line there, but there'll be a gap there that looks at. And then we'll have this horizontal asymptote at 1, so y equal 1, x equal 4. And then from here we can sketch the graph in. There's only really one way the graph can fit here. This is a rational expression, so I know that it's going to look something like this. So this is my graph. Now it definitely passes the horizontal line test. So it passes the horizontal line test. And if it passes the horizontal line test, we say that is 1 to 1. So then we know an inverse exists. I may or not be able to find that. I think I can for this one, but we do know that it exists. So that's kind of the first thing that we do, is we check for that. And the next thing, let's go ahead and find the inverse. Still no calculus, but I want you to know that it's coming up just in case you're getting concerned. So first step, what we do is we swap the f of x with the y. Second step, we swap the x's and the y's in the equation. And then the third step is we solve for y. So there's a couple different things when we're solving for y to keep in mind. We usually like the variable we're solving for on the left, or at least I do. It makes things a little bit easier for me. So what I'm going to do is clear the fractions by multiplying both sides through by y minus 4. So these cancel. And then I'll distribute through the x, so I have xy minus 4x equal y plus 3. So again, I want all the y's over here on the left. So I have xy minus y equals 4x plus 3. So we took this negative 4x and I added it across. Okay, so now you might think, well, we're not really making much progress here, but we actually are. There's a common factor of a y here. So if I factor out a y from each term, I'm going to be left with x minus 1. And then to finally solve here, I divide both sides through by x minus 1. So my inverse be my fourth step. My f inverse of x is equal to 4x plus 3 over x minus 1. So now let's go ahead and do that domain range table. And again, there'll be a graph here that you can check, but I would just go through and eliminate the possibilities that are not symmetric across the line y equal x and plot a few points to check those. Those are pretty straightforward. But what I want to do is find the domain and the range. So here's f inverse. And then my original function was f of x equal x plus 3 over x minus 4. Let's make that domain range table. Now the reason this is so important is that the calculus portion of this, when we start talking about derivatives, relies on you understanding this part. So if I have f of x and I have f inverse of x, and then I have the domain and the range, we have to understand this part in order to talk about the calculus that's coming up. Okay, so here's my original function. So that's f of x. The domain means what are the possible x values? Well, the x values can be every single thing except what makes this undefined. And what will make this undefined is if x equal 4. Okay, so for this one, x cannot equal 4 because the denominator would be 0. Now if you think about x equal 4 on a number line, this is what that looks like. So it goes from negative infinity to 4, and then from 4 to infinity, but it can never reach 4. So this goes negative infinity to 4, union 4 to infinity. Okay, that's what that looks like. Now we know the domain and the range swap. I'm going to scoot that over a little bit so we're not crowded. So that becomes the range of my inverse function. Isn't that cool? So I already know what visually this will look like if I graph it. That will be the range. Okay, now the next thing I want to do is to figure out what is the range of my original. Well, that's tough. I'd have to graph it to be sure. It's easier to talk about the domain of the inverse and then swap it up. So if we look at our inverse, the domain again is anything that makes this fraction undefined, and what will make this fraction undefined is if x equal 1. So for this one, I have to say x cannot equal 1. So I look at my graph. Here's 1, hollow point to infinity, negative infinity. So this goes from negative infinity to 1, union 1 to infinity. And then this swaps up. So to me, it's easier to find the domains and then swap to the ranges. So that's about everything about this function. We didn't look at the graphs, but you can graph those on your calculators if need be, and then you can also figure out the inverse graph as well, and then compare them. And remember, they have to reflect across the line y equal x. Okay, so now we're getting to the calculus part. This is such a cool thing here. So let's look at derivatives and inverses. Now that we understand inverses pretty well, let's see what we're trying to get at here. Now, one of the big takeaways of this is I can't always find an inverse of a function. So how could I actually take the derivative of it if I can't find the inverse? And that's what this is kind of dealing with here. Now, the derivative gives us the slope of a tangent line, and so that's what it's focusing on, is can I find the slope of the tangent line? So I want to look at this kind of visually first. So let's look at y equal x squared, which does not have an inverse unless you restrict it. And we're going to restrict this from 0 to infinity. Notice the bracket is 0. And if we work through this, and I'll let you do the steps because you're probably good at finding inverses now. My inverse of this function, I'd swap the x and the y, take the square root of each side. Actually, let's go ahead and do that. We're going to swap x equal y squared equal x, because I like my variable on the left that I'm trying to solve for. Take the square root of both sides and I get y equal plus or minus x. And this is why I wanted to do this real quick for you. Where's the minus? Well, I'm not considering it because I'm restricted this. So I'm not going to do the plus or minus. I'm only going to look at the positive or principal root. I don't even need to write it in really. So this is square root of x. Now if we were to do a quick curve sketch, y equal x squared looks like this from 0 to infinity, and f of x equals square root of x looks like this, and we can see that it definitely does reflect across the line y equal x. Okay, so what was I going to do with this? Oh, that's right. Okay, I'm going to draw a little bit better graph than that real quick. Okay, I wasn't going to do this part, but it's so interesting. So let's look at y equal x squared. Let's plot some points. If I plug in a 0, 0 squared is 0. If I plug in a 1, 1 squared is 1. If I plug in a 2, 2 squared is 4. And if I plug in a 3, 3 squared is 9 up here. Now remember, these points reflect. So 0, 0 reflects onto itself. 1, 1 reflects onto itself. And a lot of times when I'm graphing the inverse, what I'll do is I'll use an asterisk for the inverse points just to help me visualize that a little bit better. 2, 4 becomes 4, 2, and 3, 9 becomes 9, 3. Okay, so let's go ahead and plot these points. Now this almost looks like it should be like a straight line here, but it has to curve up is the important part here. So this is going to start down here. That's not too bad. Okay, now let's look at the green, which is my inverse. And then let's look at the line y equal x. Y equal x. Okay, there we go. So this blue graph, f of x, and then this green graph is f inverse of x. So what is the calculus part of this? Well, this is the calculus part. I want to know the slope of the tangent line at this point. Well, that's easy. I know my function is y equal f of x is x squared. The derivative of 2x is, or sorry, the derivative of x squared is 2x, and then I plug a 2 in. 2 times 2 is 4. So the slope of the tangent line here is easy for me to figure out. And in fact, I could even write the equation of the tangent line. So this is the ordered pair 2, 4, and the slope here is 4. And how did we figure that out? Because y prime is equal to 2x, and I evaluate that at x equal 2. I get 2 times 2 is 4, so the slope is 4 at the ordered pair 2, 4. So that's what I found out. Well, I don't even need to find the inverse. I do have it here, but I didn't even need to find it. I could just come over here to this point for 2 that's the reflection of that, and I know that my slope is the reciprocal. That's the whole story here. Okay, notice the reciprocal, the points flip, the slopes reciprocate. Okay, so let's look at that. So for f inverse of x, what I know then is at the reflected point for 2, the slope is 1/4. And I didn't even have to take the derivative of this function. That's just going to work every single time. So let's check it because I can actually take the derivative of it. So f inverse prime of x, the notation is cumbersome. Another way you could write that is d dx of f inverse of x. That still means derivative. So that would be 1 over 2 red x. And the way we get that is, let's note up here, that would be the same as x to the 1/2. So when I take the derivative, I'd bring the 1/2 down, decrease the exponent by 1, and I'd flip that into the denominator, and that's where this comes from. Now if I evaluate this at 4, not at 2, because up here I evaluated it at 2, but remember these swap, so the 2 becomes the range down here, but the 4 is the domain. So I want to use the x value. So if I plug that in here, I get 1 over the 2 times the square root of 4. Square root of 4 is 2, and I get 1/4. That's my slope. Okay, so that's the whole story here. So what we're about to look at, though, makes it look a lot worse, but keep in mind that's all we're doing, is I'm trying to figure out the slope of the tangent line for the inverse graph at a particular point without ever knowing the function itself. Okay, so that's what we're up to. It's pretty cool to be able to do that. So the notation gets a little bit icky, but please remember that that's all we're doing. So don't focus on the notation, focus on this basic graph. If we know the function and I can find the slope by taking the derivative, I reflect the point and I reciprocate the slope. So that's all it is. Okay, so let's look at the formula for this. And I would not expect you to memorize this formula at all. It would be given to you, but honestly, it looks so complicated that I guess I wouldn't even want to see it on a formula sheet. I would just remember what we said here. If I want to find out about the derivative of the inverse of a function, all I need to do is to find the derivative and evaluate that regular function, my function f of x, and then reciprocate the slope at the flipped points, and I'll know exactly what I need to know. So here's the formula, though, just so you can have it. So this is going to look like the derivative of f inverse, and I'm just going to call this evaluated at x equal b. And remember, the ordered pair that we were looking at for my original function was ab, so when I swap it, it's ba. So this is just going to be equal to the reciprocal, so 1 over the derivative with respect to x of my function f, evaluated it at x equal f inverse of b. Look at that. Okay, so we understand what it means, thank goodness. We don't have to rely on this formula. We just need to remember that if I can find the original slope, I can reflect the point and reciprocate the slope. It's no worse than that. So let's look at an example of when we can use that and how to use it. But again, don't get tied up in the formula on this one. The notation is just super user unfriendly there. Okay, let's have a look at this one. So we're given a function f of x equals the 4x cubed minus 7x squared minus 6, and we have a restriction here. So let's keep in mind that restriction. We'll talk about that when we look at the domain and range swap if we need to. First of all, what I'd like to do is to establish if an inverse exists. So I graph this. You can graph this on your calculators. You might have to adjust the window quite a bit on this one. It's kind of a crazy graph. But if you notice, this does not pass the horizontal line test. So right here is a big problem. Does not pass the horizontal line test, and even right down here a little bit it wouldn't. So what this restriction did is they said, I want to restrict this graph from 1.5. So here's 1. So 1.5 is right here. So I'm only looking at this portion of the graph because it said 1.5 to infinity. And so we can see on this part it does pass the horizontal line test. So it's restricted. And if we look up here, see it says greater than or equal to 1.5. That's why the graph was restricted. Otherwise the inverse wouldn't exist. Okay, so let's kind of start with that premise. Okay, let's go ahead and try and find the inverse. So it is 1 to 1 on the interval 1.5 to infinity. So an inverse exists there. So let's go ahead and find that inverse. Okay, so first step, you swap the f of x with the y. So I'm going to have y equal 4x cubed minus 7x squared minus 6. Second step, we swap the x and the y. 4y cubed minus 7y squared minus 6. Now the next thing is solve for y. Well, that's the problemo. I cannot get y by itself. I don't have any techniques to help me do that. So an inverse exists right over here. It says so. But over here it's saying, yeah, it exists, but I can't find it. What we'd have to do is plot points and get a picture of it, a graph of it, just by flipping points. But I'm not going to be able to write a function that defines it. So cannot find the inverse. But we do know that it exists. I could graph it, but I can't find a function. Okay, so now this is where this is all going to come into play. I want to figure out what is the slope of the tangent line of my inverse graph at the reflected point that they give me here. So that's what I'm working toward. So if we look at this graph, 4x cubed minus 7x squared minus 6, they're giving us the point 39 and then f of 3. And this is a little bit confusing for this notation. So I'm going to come down here and let's talk about f of x and f inverse of x, domain and range. Now remember, the domain and the range swap. So this is our input value right here. This is our domain. So 3 is the domain of my original function, and then my range is 39. So this swaps. So this becomes 39, this becomes 3. So this is kind of our big crucial piece of information here. Okay, so let's get to work down here, trying to not necessarily focus in on that formula, but kind of thinking our way through this. So if I could find the slope of the tangent line to f of x, my original function, at the point, and again that point was up here, it is 339. Then what I should be able to do is find the slope of the tangent line to my inverse, this is vastly superior to think through this rather than use that formula, to f inverse of x at 39.3. Okay, so but before we can do the inverse, we have to do the original. So let's pop over to the original. So our original function again was f of x equals 4x cubed minus 7x squared minus 6. Now my derivative is then 12x squared minus 14x, and I want to evaluate this, at 3. And why at 3? Because that's the point they gave me to evaluate it at. So let's go ahead and plug a 3 in there. We're going to have 12 times 3 squared minus 14 times 3. Okay, 3 squared is 9. 12 times 9 is 108, and then 108 minus 14 times 3 is 42. So when I subtract those, that's going to give me the slope, and I'm going to get 66. So f prime of 3 equals 66. This is the slope of, or the slope at, I'm going to say the slope at 339 on f of x. Well, we know our answer over here already. At 39.3, then our slope is equal to the reciprocal. Okay, so it would be the reciprocal of the slope at 339 on my original function f of x. Well, that's just 1 over 66. Okay, that's all it is. Now if we were to graph the function and its inverse, but again, I don't have the function, so it's hard to graph it. I'd have to go point by point, but I could do it. I'd have to look at a lot of ordered pairs, but this is that slope that we'd be looking for. And we don't even know the inverse function, and we were still able to figure out the slope at a particular point using the fact that the reciprocal point, or the reciprocal slope, is at the reflected points, 339, 39.3, 66, 166. So I really enjoyed this section. When I first started looking through it, I did not like that notation. I don't like that formula a lot because it's a little bit more confusing. It almost makes it seem worse than it is, but it's really not that bad. So hopefully you enjoy this nice college algebra review of inverse functions, finding inverse functions, looking at the properties of inverse functions, and then throwing in this calculus bit at the very end about the swapped points and reciprocal slopes. If you ever have any questions, as usual, I'm always happy to help. Please pop into my office hours either on campus or online. I'm also in the slide rule. You can stop by the slide rule. And even if I'm not there, you're welcome to go to the slide rule. No appointment necessary. Just drop in, ask for help. It's a great spot to go do your homework even if you don't have math questions. So if you do have a math question, somebody's there to answer it, and you don't have to pack up all your gear and head across campus or head into town to get some help. Always available to help, so please make sure you ask questions when you have them. Hope you enjoy this assignment. I know that I did.